I'm Timothy Priscilla, and we're still doing linear programming with my Math 1324 class. We're using the graphical method again on this example. We want to maximize and minimize z equals 9x minus 9y, subject to, notice my abbreviation for subject to. Some people use this symbol here. And invariably then people, oh y'all can't see it there. Invariably people then want to know what it is, so I just do the ST abbreviation. And here are my constraints. 4x plus 3y is less than or equal to 20. 4x plus 5y is less than or equal to 30. X is bounded between 0 and 5 inclusive. Y is bounded between 0 and 8 inclusive. One thing that stands out here is I don't see a statement of non-negativity constraints. For linear programming, x and y cannot be negative. That's what's happening right here. This is saying x is greater than or equal to 0 and y is greater than or equal to 0. So the left-hand side of those two compound inequalities is saying our graph is going to just be in quadrant 1. Now, I'm going to go in a different order. I'm not going to just start at the top and go down. I'm going to deal with those compound inequalities first. Looking at the green one, x less than or equal to 5. We have to graph the line x equals 5. From your previous math classes, when you were graphing lines and there was only one letter, it was one of the special cases, either a horizontal or vertical line. In this case, there's an x and no y. What sort of a line is that? All of the x coordinates are equal to 5. What would that be? Vertical line. Okay, so that's a vertical line passing through 5. So I'll come over here to my to my graph paper. There I am. The Math Learning Center web page has graph paper that you can download or print out if you want graph paper to do your graphing on, or you can just search on it, do a Google search. There are plenty of places online that have free graph paper for you to download and use. So what did we say? It was a vertical line passing through 5. 1, 2, 3, 4, 5. There's 5, and this was the green line. There it is. That's the x-axis. Here's the y-axis. Okay, there. That's the x-axis. There's the y-axis. And we just drew the vertical line passing through 5. Now, we want to shade the region where the x values are less than 5. Here's the vertical line. I'm not even going to choose an ordered pair and test. I know which side has the x values less than 5. Is that to the right or to the left? To the left. So we've shaded this area out here. We've shaded that area out there. We mentally shaded it. I'm not shading it. I'm not writing it out just because. I'm not going to write it on the paper, the shading, because then it just starts getting too messy. Now we need y less than or equal to 8. So we have to graph the line. We're graphing this inequality, y less than or equal to 8. We have to graph the line y equals 8. Well, what sort of a line is that? There's only one letter, the y. We want the line with all the y coordinates equal to 8. So that is a horizontal line. Okay. 1, 2, 3, 4, 5, 6, 7, 8. You draw your horizontal line there. So that's a horizontal line. And instead of choosing an ordered pair, I can do the testing in my head. Which side of that pink line are the y values less than 8? Above or below? Below. So at this point, what region has been shaded both times? I am going to do the shading now. At this point, we have this closed bounded rectangle. There. That's what we have as our feasible region up to this point. But that's not, we're not through drawing the feasible region yet. We still have two other inequalities that I delayed graphing. The blue one and the purple one. 4x plus 3y is less than or equal to 20, and 4x plus 5y is less than or equal to 30. Let's do 4x plus 3y is less than or equal to 20. 4x plus 3y is less than or equal to 20. So we need to graph the line 4x plus 3y is equal to 20. So often the intercepts turn out to be corner points. That's why I find the intercepts to draw the graph rather than writing in slope-intercept form and using rise over run. So you usually need to know those intercepts anyway. When x is 0, what's y? Nope. 20 divided by 3, I'm getting 20/3. And when y is 0, what's x? 20 divided by 4, I agree with 5. Okay, and 20/3. That's what, 6 2/3? Yeah, that's 6 2/3. So maybe I'm going to make a note of that because that'll make it easier for me to label on the y-axis. So here's my graph. We're going to go right, left, right, 0, up 6 2/3. So there's 6 right out there. I'm going to make a note. That's 6 2/3. And then I go, oh, this is nice. 5, 0. It's the same corner point at least. Draw my boundary line there. Now what do we need to do? The shading, okay, how do we decide where we're going to shade? Are we going to shade to the right of the blue line or to the left of the blue line? How do we make that decision? Here we'll test, choose a point that's not on the blue line. What point do you think I'll test? Yeah, I'll test 0, 0. Plug in 0 in for x and 0 in for y into the original inequality. We're going to get 0 plus 0 is less than or equal to 20. True or false? True. So we shade the region towards the origin. We shade towards the origin. So at this point, what have we got shaded? This little triangle? Maybe it'd be a good idea. Where's my eraser? I'm going to erase this thing here that's no longer shaded. There. Watch me tear the page. There. So far, we shaded towards the origin. So the region that's been shaded every time is that little triangle. Oh, it's a pretty big triangle, actually. Are we finished with the feasible region? No, we have one more inequality. Which one do we still have to do? 4x plus 5y is less than or equal to 30. We need to do this one. So 4x plus 5y is less than or equal to 30. We have to graph the line 4x plus 5y equals 30. When x is 0, y is 6. When y is 0, x is 15 halves, 30/4 reduces to 15 halves. In a moment I'll be labeling that on the x-axis, so maybe I'll think of it as a mixed number, 7.5. So we have to label 0, 6, and 15 halves 0. 0, 6, oh, that's down right there. And 15 halves 0, that's 5, 6, 7.5 right there. Draw the line. Testing 0, 0, do we get a true statement or a false statement? We get a true statement, so we shade towards the origin. Testing 0, 0, we get a true statement, so we shade towards the origin. And do y'all see what region's been shaded every time? We no longer have, let's see, we have, I guess the only thing being discarded is this little bitty triangular wedge right up here. So there's my feasible region. There's the feasible region. I labeled that, of what was that, 20/3, that 6.5 here. That point there, is that going to be a corner point though? What's the corner point on the y-axis?
6, 0.
I think it's 0, 6. 0, 6. It's that lower point there. It's hard to tell because notice how close they are together. But I have corners. Let's write my corners out. I have 0, 6. You move down, you're ready to change lines, so you have another corner. This corner is 0, 0. You move right until you're ready to change boundary lines. We have another corner point at 5, 0, I agree. Now we're moving along that blue line, and there's a corner point right there. It's hard to tell it, but there's a corner point right there, and it's formed by the purple and the blue lines. So we're going to have to use elimination now. The purple and the blue lines. Let's see, the blue line was 4x plus 3y equals 20. And the purple line was what? 4x plus 5y equals 30. And what do y'all want to do? Elimination, which variable do you want to get rid of? X, yeah. Why don't we do something so that we get rid of the negatives? I'm going to multiply the first one by -1. Multiply the first one by -1 and add the two equations together. What are we going to get? We'll have, that's a -4x plus 4x. That's okay, so we've eliminated the x's. That'll become a -3y plus 5y. That becomes a positive 2y equals, that's going to be a -20 plus 30, positive 10, and that gives me a y value of 5. Oh, okay, that's nice. So we know that the third corner point is going to have the fourth corner point is going to have a y value of 5. So when I'm listing my corner points, I know the y coordinate for the fourth corner point is going to be 5. How do I find the x value? Plug it in. Okay, so I guess I'll just plug it into the first one. We had 4x plus 3y equals 20. We're going to plug in what? I'm going to plug in 5 for y. So that's a 4x plus 15 equals 20. So 4x equals 5. 20 minus 15, I agree with 5. So what are we getting for x?
X is
5/4. Oh goodness. Let me see. Yeah, I dropped my work. So x is 5/4. 5/4 right there. So remember my what my little feasible region looked like. Here it was. We were able to see 0, 6, 0, 0, and 5, 0. That corner point right there that's so hidden, turned out to be 5/4, comma 5. Does that look like 5/4 5? No. No, it doesn't. No, it doesn't. So 9x minus 9y. Oh, and by the way, this is like y'all's, what problem number was this? This is like y'all's number 8. Okay, so this is like the number 8 in your current homework. So plugging in 0, 6, what are we getting for p? We'd have a 0 minus 54, which gives me a p-value of negative 54. Plugging in 0, 0, what are we going to get for p? 0. Plugging in 5, 0, what are we going to get for p? 45 minus 0, I agree with 45. And finally, plugging in 5/4 5. That's 9 times 5/4 minus 9 times 5. That's going to give me a... okay. So let's see. Maybe we'll want to... yeah, I'm going to write it as a decimal. Negative 33 and 3/4. So negative 33.75. We have a closed bounded feasible region. Do we even know that a maximum and minimum exists for a closed bounded feasible region? Yes. For closed bounded, both of them exist and they occur at corner points. So the biggest p-value is the maximum, the smallest is the minimum. What's the biggest p-value? 45. That's the maximum. It occurs at the corner point 50. What about the minimum? The negative 54. Negative 54, and it occurs at the corner point 06. So we have a maximum at, our maximum is negative 54.
No, it doesn't.
Oh, pardon me. Our maximum is 45. The minimum is negative 54. For my final answer. Okay, bye. I think I'm going to take a break.